All right, folks. I just want to go over the last exercise here. It's a little interesting. It's I think a little intensive. It's the first time we're going to really prove something I think really deep about a set of functions that we defined forever ago on day 3. So what I have here are our definitions of incr, bin to nat, nat to bin, double bin, and normalize. So these are the functions that we use that let us sort of move back and forth between binary numbers and natural numbers, do various things with them. Um, what I want to do here is make formal some arguments we made a while back. We were very interested in like, well, how does it go? Round tripping, what do these operations mean? Did we get it right? And it was really tricky to find out how to do that. So we can use proof as a way to build our confidence. The first proof I'd like us to do is a sort of correctness proof for incr. If I have a binary number, call it b, and I run incr to get another binary number, call it b prime, and then I convert it to a natural number, call it n, that should be the same as if I take that same binary number b, convert it to some other binary number n prime, and then take the successor of it, right? It doesn't matter whether I increment, that is to say add 1, and then convert to natural, or if I convert to natural first and then just add 1 using successor. This kind of diagram is called a commuting diagram, and people use them all the time to represent sort of a theorem. This is sort of a visual rendition of what we mean by a theorem. So the idea being that it doesn't matter whether you traverse the top row and then go down, or go down and then cross, you'll end up in the same place. You'll get an equal answer. So we'd like you to translate this graphic to a theorem. We'd like you to name that theorem bin to nat pres incr. The pres here is sort of for preserves, right? Bin to nat preserves the meaning of increment. And we want you to fill it in all by yourself here. You can do the whole theorem declaration yourself. Please just name it this. It'll make our lives easier. Next, we want you to prove that if you take a natural number and convert it to a binary number and then convert it back, you get back exactly the same number. Okay, and then lastly, we want you to prove that you can go the other way. You can take a binary number, convert it to a natural, and then convert that natural back to a binary number, and it won't be exactly b. No, it'll be normalize b. Right? This was the normalized function we asked you to write to find the sort of canonical form. So bin nat bin is a theorem that will have you proving that you can almost do a round trip in the other direction. Okay. If you have any questions about any bit of this process, feel free to ask us on Zulip. You're probably going to need to define your own helper lemmas. And to do that, you have to think about what properties you want and which properties you can prove and which properties will help you get where you're going. This is a challenging process, and I don't know a good way to learn this part of the process other than looking at other helper lemmas, say the way plus NSM supports plus com, and then just sort of thinking about what it is that you need to be true. It's a very challenging skill, the same way that coming up with good helper functions is a very challenging skill. Um, I'm here to help you though, so hit me up on Zulip and we can talk about it in class too. I want to conclude with a micro sermon. You've got a bunch of tactics now. And with induction, you now have like the power tool of computer science proof. So it's really easy to just like fire off tactics. And on simple proofs, that'll work, right? Like if we're going to be real, most of the proofs in this file can be done by like induction, simple, a rewrite or two by the IH, and then reflexivity. Maybe an apply here or there, maybe a lemma, maybe. Right? A lot of the proofs are in structure not that complicated. And then you might just sort of like stumble into whatever else you need and feel confident just based on that. But I want you to really resist the temptation to just like video game using cock. The more you video game, the less you're going to be able to track what's really going on. And then as things get more complicated, you're going to be out to sea. Okay, if you are stuck, the thing to do is to try to get unstuck using examples, not by doing more proof, but using examples to understand why the property is true, or maybe why your helper lemma isn't true. If you're stuck for more than 20 or 30 minutes, drop us a line on Zulip. You should not be sitting and spinning your wheels. Let us help you figure out what it is that's getting you stuck. That's what we're here for. All right. I hope y'all have fun with this. Should be pretty interesting. I'm curious to see what y'all make of all this induction business. Talk to you soon.